Hi guys, today we'll discuss a geometry problem from Waterloo's Grade 10 Cayley contest. This is question number 23 from year 2007. Starts off with a diagram and the question goes, ABCD is a rectangle with AB equal to 12 and BC equal to 18. Rectangle AEFG is formed by rotating ABCD about through an angle of 30 degrees. What is the total area of the shaded region to 2 decimal places? This question requires a solid understanding of trigonometric ratios. If you're in Ontario, then you should learn this topic by around the second half of grade 10. We're not going to go through this topic in details today because there are many materials on this and I'm making a future video that explains this in details. Today we're just going to do a crash course on how to apply this in problem solving. On a high level, trigonometric ratios outline the relationships between the angles and the sides in right triangles, right? Suppose I give you a right angle triangle and I give you one of the other two angles, let's call it theta. From the perspective of the theta angle, we can name all three sides of this right angle triangle. And we know that these three sides, they must follow some kind of ratio. And these ratios depend on how big theta is. And these three ratios are sine of theta, cosine of theta, and tangent of theta. Let's illustrate the application through an example. Suppose I give you a right angle triangle and give you one of the other two angles, let's go 15 degrees, and I give you the length of the side adjacent to the 15-degree angle. We can calculate the other two sides using trigonometric ratios and a calculator. Take your calculator, punch in cosine of 15, and that gives you 0.966. which is the ratio of adjacent to hypotenuse. We already have the adjacent, so we can calculate the hypotenuse, which is 12.423. We can also calculate the opposite side. Type in sine of 15, that gives you 0.259, and that is the ratio of opposite over hypotenuse. We just calculate the hypotenuse, so we can calculate the opposite, which is 3.215. Of course, you could have calculated this using tangent ratio as well. Type in tangent of 15 degrees, that gives you 0.268, and that is a ratio of opposite over adjacent. We are given the adjacent, which is 12, so we can calculate the opposite using 12 times 0.268, and that gives you 3.215, same as the sine calculation. So that's enough knowledge for today. Now, back to this question, we're asked to calculate the area of some complex shape. And the basic idea is to cut this complex shape into simpler shapes that you know something about. And the problem is, how do you exactly cut this, right? Well, when you're facing a geometry problem, a good first step to take is to label everything you know about this complex shape. So let's start with the sides. We know that AB is equal to 12, right? And AE is the same as AB, so that's also equal to 12. And so is GF, this is also 12. BC is equal to 18, right? That means AD is also equal to 18, right? AG is also 18. So that's it about the sides. Let's talk about the angles. We know that you're rotating about through an angle of 30 degrees, which is this angle, BAE. This is 30, right? Which is also this angle, right? So DAG is also 30 degrees. And because BAD is a right angle, if BAE is 30, this angle here must be 60, right? And I know these are right angles. So AEHD is a quadrilateral. We know that the sum of all interior angles in a quadrilateral is 360 degrees, right? So this angle DHE must be 120, right, to make this 360. Since DHC is a straight line, then this angle right here must be 60 degrees, right? And the opposite angle of that, which is DHF, that must also be 60 degrees. And we know that all these angles are right. So we have all the information we know. Another important observation to make is that the shaded area ABCHE, this area on the bottom, is actually the same. The area is the same as the shaded region on the top. All right, why is that? Because both ABCD and AEFG started off as the same rectangle, right? And then you got the same chunk, this unshaded white region, taken out of them. So if they start as the same area, then you got the same parts taken out of them, and then whatever is left must be the same. So therefore, I don't have to cut both shaded regions, right? I can just calculate one of them and multiply by 2. Now, at this point, we can see that there are actually two general approaches to this problem. The first approach is what I just showed you. You can take one of the shaded regions, cut them down into simpler shapes, so you can calculate the area of the shaded region, then multiply by 2, since both the top and bottom shaded regions have the same area. In the second approach, right, if you think it's easier to cut the white unshaded region, then you can calculate that area first, then take a rectangle, subtract that, then you're left with the area of one of the shaded regions, then multiply that by 2. It will still get you the same answer. We're going to start with approach 1, and this is the approach that's the most intuitive to me. Take the length EH, right? Extend this line down onto BC and let the point of intersection be called O. I have cut this lower shaded region into a right angle triangle OHC, and that is a 30, 60, 90 degree right angle triangle, and a quadrilateral ABOE. You can see that ABOE is actually a symmetrical quadrilateral because AE is equal to AB, they're both 12. Angle ABO is the same as angle AEO, they're both 90 degrees. So ABOE must be a symmetric shape. If I were to draw a line between A and O, then A will be a bisector that cuts the angle BAE into halves and splits ABOE into two identical right angle triangles. So I can calculate the area of one of the triangles, right, using trig ratios, then multiply that by 2 to give me the area of the quadrilateral ABOE. So let's do that. If AO is the bisector, that means BAO, this angle must be 15 degrees, right? From the perspective of this 15 degree angle, OB is the opposite, AB is the adjacent. We're given the adjacent, so we can calculate the opposite using the tangent ratio. Punching tangent 15, you get that OB is equal to 3.2154. Now you have the base of the triangle, which is OB, you have the height, which is AB, then you can calculate the area of ABO as base times height over 2. If you want the area of the quadrilateral ABOE, just multiply that triangle by 2, so you have the area of the quadrilateral ABOE as 38.5848. I'm keeping this many decimal places because the answer requires you to be accurate to 2 decimal places. Now all we're left with is this 30, 60, 90 degree triangle to the right. We know that BC is 18, right? We just calculated the length of OB, right? So we can calculate the length of OC. Just take 18, subtract OB, and that is the length of OC, which is 14.78. And take the perspective of the 30 degree angle on the bottom. Use the tangent ratio to calculate the length of CH, and that is 8.5. So you have the base, you have the height, calculate the area of OCH, and that is about 63.1. Now piece these two shaded regions together, then you have the entire shaded region on the bottom, which is 101.68. And then multiply that by 2 to get both shaded regions areas, and that is about 203.3694. Now let's move on to the second approach, which involves cutting the white unshaded region into simpler shapes. So take a look at the white unshaded region AEHD, right? We know the length of AE. We know the angle EAD, which is 60 degrees, right? Now draw a perpendicular line from E to AD and let the point of intersection be called O. Then we see that AOE is actually a 30, 60, 90 degree triangle. So we know the length of AE. You can easily calculate AO and OE. From the perspective of the 60 degree angle EAO, then AO is the adjacent, AE is the hypotenuse, right? I can calculate AO using the cosine ratio, and that gives you 6, right? So AO is equal to 6. And we can calculate OD because AD is 18, so just subtract 6 from 18, you're given the length of OD, which is 12. We can calculate the length of OE using the sine ratio, and that gives you OE equal to 10.39. So we have the base of AOE, which is 6, and I have the height, which is 10.39. I can cut the area of AOE triangle, and that is about 31.1769. So all we're left with is this trapezoid to the right. We know the lower base of this trapezoid, OE, that's about 10.39. We know the height of this trapezoid, which is OD, that is 12. All we're left with is just the length of DH. Now we can calculate the area of this trapezoid. So how do we find the length of DH? That requires another assisting line. Draw a perpendicular line from H to OE and let the point of intersection be called P, right? So we know that OD is equal to PH. They're both 12. And I know that PEH is actually a right angle triangle, 30, 60, 90 degree to be exact. And I know the length of PH is 12. So I can easily find the length of PE, right? So PE, you can use the tangent ratio from the perspective of the 60-degree angle PEH. You can find that PE is equal to 6.9282. Once you have that, you can calculate the length of OP, which is the same as DH, right? So the length of DH is 3.4641. Now the area of a trapezoid is the lower base plus the top base times height over 2. So you do 10.39 plus 3.46 times 12 divided by 2. That gives the area of the trapezoid 83.1384. Therefore, this entire unshaded white area is 31 plus 83. That's about 114.3153. Now take a full rectangle, right? 12 by 18, subtract this unshaded region, then you're left with one shaded region. Then multiply by 2, you get both shaded regions, and the area is still 203.3694.